Howdy, folks. Well, welcome to part two of nuclear chemistry. Well, just a reminder, in part one, we talked about the stability of the nucleus and what makes a nucleus stable, even numbers of protons and neutrons, or the magic numbers of protons and neutrons that seem to be extremely stable. So we talked about some generalities that might bring about stability in the nucleus. But then that also pointed to the idea that when a nucleus becomes unstable, there are certain mechanisms by which it might bring about its own stability by ejecting parts of itself. For instance, like in the ejection of alpha particles for those elements that were atomic number greater than 83. So again, that was one of those things that brings about a nuclear instability, is getting too many protons in one place. We talked about beta emission. This happens when, in a particular isotope, the neutron-proton ratio is higher than normal, than what you'd find in the band of stability that we discussed. And so beta emission usually occurs in those cases. We looked at electron capture and positron emission. This usually happens when the neutron-proton ratio is lower than normal, on the south side of that band of stability. And we looked a little bit at gamma radiation, how it accompanies a lot of the emissions of other nuclear particles. Okay, so we looked at those mechanisms, and I showed you that band of stability that's kind of a nice predictive graph of knowing that if you're on the north side of that band, that very likely you're looking at a potential candidate for beta emission. But on the south side of it, it was positron emitters and electron capture mechanisms. And anything above atomic number 83, again, was a potential alpha emitter. All right, well, I mentioned at the end of part one that we were about to talk about exposure to radiation and detection. So let's start there with detection. All right, well, the book discusses several methods for measuring radiation, but the primary one that you find in the chem labs or in the physics labs is a Geiger-Mueller counter. Now, a Geiger counter is pretty simple, the way it actually works. It's a can filled with argon gas. There's a high voltage DC power source connected, putting a negative charge on the outer can with an electrode that goes down into the sealed can filled with argon gas that's positively charged. The opening in the bottom of the detector probe is made from mica. Mica is a crystal that has large interstitial spaces in it. It's a lot like asbestos, as a matter of fact. The crystal structure is kind of amorphous. It's not a regular crystal structure. Consequently, it leaves large gaps in the structure. And particles can actually go through there. Well, it turns out that alpha particles and beta particles are very small. And so the interstitial spaces in this mica window will allow them to pass through. However, argon atoms are much larger because of the size of its nucleus, a big atom. It can't get out through the mica window. So we can trap it in there, but still allow alpha and beta particles to sail right through that little detector window. Well, whenever an alpha, a beta, or a gamma photon, for instance, enters that window, it ionizes one of the argon atoms that's in there. And in doing that, once it steals the electron from that argon atom, that argon cation immediately crashes into the wall of the can. The electron crashes into the electrode that's in the center of the can, and there's a detector built into this system that detects that little glitch in voltage and counts that as one count. So essentially then, a Geiger counter just counts how many radioactive particles came in per minute. Usually it's given, it counts per minute. All right, now we usually find that even in the lab, when we turn on the Geiger counter, just the background radiation in the room, and again, there's a lot of naturally occurring radioactive isotopes that are on the planet. Now, it's funny, when you say the word isotope, usually the word radioactive kind of ties in with it. Not all isotopes are radioactive, remember. An isotope is just an atom that has different numbers of neutrons. However, the radioactive isotopes that do occur on the planet, from those original three parents I discussed in part one, have now given us an array of different radioactive particles that are kind of scattered and stirred into everything here on the planet. So everything in this room, everything that it was in the lab room, the concrete blocks, it contains radioactive isotopes, small quantities, but enough to give us a background reading in the room of about 70 counts per minute. And so, again, whenever any reading was made for an experiment, we had to pretty much subtract off whatever the background reading might be. All right, well, now that we've looked at, just the machine of how we actually detect radiation, let's look a little bit at biological exposure and some of the units that we use for measuring radiation. Okay, in part one, I talked a little bit about exposure and shielding when I was talking about alpha particles. I mentioned that they're big and slow, and consequently, you can actually stop them with a sheet of notebook paper. So penetration skin-wise is not a big deal. The big deal is when they're inhaled or ingested, or you inhale a gas, for instance, that's an alpha emitter. For instance, like radon. It's become an issue over the last few years since we've detected it percolating up through our basements. And again, it's an alpha emitter, and if you inhale that radon, then suddenly you've inhaled an alpha emitter. Alpha particles, remember, are strong oxidizing agents. They'll steal electrons from whatever they touch, and so consequently, not good for you. All right, so harmful if inhaled or ingested. On the other hand, beta particles, a little more penetrating. They're faster. You can get a surface burn from exposure to beta radiation, but you can stop them with a heavy-duty aluminum foil. They're not all that penetrating, and so consequently, just wrap yourself head to toe in aluminum foil, you'll be fine. And I've heard that that stops the alien mind probes also. But again, a little bit more penetrating than the alpha particles. Now, not necessarily more dangerous. The danger with the alpha particles, again, is that inhalation of the alpha particles, and they pose really quite a bit of danger in that respect. Now, gamma radiation, though, just in terms of penetration, the most deadly. This is just high energy electromagnetic radiation. It can cause the disruption of genetic information that's encoded in the nuclei of cells as it passes through the nucleus. And so consequently, it can give rise to all kinds of weird cell mitosis. And again, radiation affects those parts of you where there's already rapid cell division. For instance, your digestive tract, reproductive organs, things like that are more susceptible to exposure to radiation than things like, for instance, nerve cells, which don't undergo very rapid cell division. All right, so basically this is the hierarchy. The alpha particles, big and slow. The beta is a little bit more penetrating. Gamma, you need a foot of lead or several feet of concrete to stop it. As a matter of fact, the lab that we usually do, and I'll try to work up a good demonstration for this, I have an alpha, beta, and gamma source that I put in our Geiger counter, and then I put shielding materials in between. It turns out that, yeah, I can put a sheet of notebook paper in between the alpha source and the Geiger counter, and all I'll get is the background radiation. With the beta, no, the notebook paper won't stop it, but the aluminum foil generally does. And then with the gamma, I've got a 1/4-inch slab of lead I put on there, and the gamma radiation sails through it like it's tissue paper. And so, again, this is why gamma sources, things like exposure to X-rays, which again are down at that high energy end of the spectrum, these are things you definitely want to minimize. All right, well, with this idea of exposure and shielding, we need to look a little bit, well, how do we actually measure this? I mean, what units of measurement do we use to measure, well, how active is the radioactive isotope? How many disintegrations is it doing per minute? Or if we take into account its penetration effect, if it's gamma, it penetrates more so than alpha or beta. So when we look at biological damage and the effect of exposure to radiation, we have to take several factors into account. All right, well, let me get rid of this and we'll discuss it. All right, well, this first unit of measurement that they use for looking at radioactive isotopes is just a measure of the activity of the radioactive sample, meaning how many disintegrations are happening per second, regardless of whether they're alphas, betas, gamma emissions, just how many nuclei are actually transmuting each second. Well, it turns out if you have 1 gram of pure radium-226, it actually exhibits 3.7 times 10 to the 10th disintegrations per second if you have 1 gram of pure radium-226. They refer to this as 1 curie of activity. And so again, activity, just simply the measurement of the speed at which disintegrations are happening, is measured in this unit named after Marie Curie. And again, they used her isotope, the radium-226, as kind of a standard of measurement for the Curie. Now again, this doesn't really point to biological damage. All it measures is the actual number of disintegrations. So again, depending on the type of radiation, one might be more dangerous than the other. So this doesn't really point, like I said, to biological damage, just to activity. But let me show you another one. All right, now this unit of measurement, the rad, this does point toward biological damage because it addresses the amount of energy that's imparted to you when a radioactive particle hits you. All right, now by definition, a rad is equivalent to 0.01 joules, 1 times 10 to the minus 2 joules per kilogram of body tissue. All right, so say you weigh 50 kilograms and you're exposed to 1 rad of radiation. Well, 1 rad is this many joules, 50 kilograms times that, half a joule. Not a lot of energy. But again, that doesn't really address the true biological damage because it depends on which type of radiation was that you were exposed to. If you were exposed to that much energy and it was alpha and it was just skin exposure, that's nothing. If you're exposed to 1 rad of energy, however, and it was gamma radiation, much more penetrating and much more likely to cause problems in the nuclei of cells that it may have passed through. All right, so even though the rad does come a little closer to looking at biological damage in terms of energy that's imparted, it really doesn't hit the nail on the head. But this next unit does. Okay, well now we're getting down to the nitty-gritty of things here. The last unit we're going to look at, the REM. This does measure biological damage. And the acronym stands for the Rankine equivalent in man. This guy Rankine, he was the guy who developed the fluoroscope, the X-ray machine, back in 1895. First X-ray they took 1899. They took a picture of his wife's hand. She had shut it in a carriage door and she'd broken her fingers. And so whenever you see anything written about Rankine, you always see this picture of this very first X-ray that they did, and it's his wife. Now, most of you don't remember this, but when I was growing up, they used to have X-ray machines in the shoe departments of department stores. And if you tried on a pair of shoes, you could actually put your feet in the bottom of this tall fluoroscope, and you could look down in an eyepiece and see an X-ray of your feet and see how scrunched up your toes were. They finally realized that this was probably not good for the public health, and those were eventually removed from JCPenney's. But it surprised me in hindsight, that they just left an X-ray machine sitting there on the floor on all the time, and people walking by and exposed to X-rays. All right, well, it turns out that the REM is actually a product of the energy that's imparted to you, the rad, that unit of measurement for measuring the number of joules, but they multiply it by something called the RBE, the relative biological effectiveness. Now, what I call that is, or I refer to it as the badass factor. Every form of radiation, alpha, beta, gamma, positron, they have a different RBE associated with them. And you wouldn't think this, but the alpha particle actually has a pretty high RBE. Not so much because of energy that's imparted to you when it hits you on the skin, it's more the inhalation of the alpha particles. So this really takes into account its biological damage, and it's multiplied then by the amount of energy. Now this tells us then the number of REMs of exposure. And occupationally, they limit you to 5,000 millirems per year, 5 REMs. So people who work in nuclear medicine or on nuclear power plants, they wear those electret badges that tell you how much radiation that you've accumulated over a span of time. And again, they'll rotate you out of your exposure area if you exceed that 5,000 millirems. But again, this is just a guess. I mean, when we're guessing how much exposure is safe, it is just a swag, a scientific wild-ass guess. At this point, I'd say no amount of radiation should be considered completely safe. And so 5,000 millirems is probably just their best guess. All right, now, when you look in the book and they talk about exposure to large bursts of radiation, for instance, an exposure to 50 REMs, that's 10 times a yearly exposure occupationally. If you get one blast of 50 REMs, you get immediate signs of radiation poisoning, nausea, hair loss, drop in the white blood cell count. 100 REMs, you see the white blood cell count go to 0, and your immune system's completely compromised. At an exposure of 500 REMs, that's 100% fatal to humans. And so again, even though we have 3 different units for measuring radiation that I've showed you here, and there's other subtle units that the physicists use also, but the Curie only shows you activity, the rad only shows you energy, but the REM is the one that really shows you the true biological damage, and that's how we measure it. All right, well, earlier I mentioned that the kinetics of radioactive decay are all first-order kinetics because there's only one reactant. And so this is going to take us back to that very first chapter we did on kinetics, and we're going to look at the first order time concentration equation because that pretty much governs radioactive decay. All right, so let's look at radiation kinetics. Okay, since we're talking about dosage, and I mentioned that 5,000 millirem limit for occupational exposure to radiation, I should point out that we're all getting exposed all the time. The background radiation just from the ground, from the sky, that comes in from space, and from natural radioactive isotopes that occur inside us, that we're exposed to about 100 millirems per year. Another 200 from the radon that's percolating up out of the planet. So 300 millirems approximately per year you're exposed to just walking around. But then again, we do a lot of medical images and X-rays, and so naturally there's medical exposure. For instance, like a dental X-ray, about 80 millirems for those bite wings. A little less if they do the panoramic thing. 200 millirems for a CAT scan of your head, and a CAT scan of your abdomen and your pelvis about 1,000 millirems. A mammogram, 140 millirems for every image. So you can see that it can accumulate. And it wouldn't be hard to approach that 5,000 millirem limit. And so again, anytime that you can minimize your exposure to any kind of radiation, all the better for it. You're all the better for it. And again, it's because a lot of this ionizing radiation causes the formation of free radicals. They can really tear you up. So again, just minimize your exposure. Okay, well, the kinetics of radioactive decay. Now again, I mentioned that this is all first order, which kind of makes sense because with the radioactive decay, you only have one ingredient. And so consequently, it couldn't be anything but first order. Way back in that chapter on kinetics, we derived a series of equations called the time concentration equations. We did it for zero order, first order, and second order. Well, the first order time concentration equation that we were most familiar with was this one here on the top. Only at that time, we used the natural log of A at time t, where A was our reactant, A at time naught. I substituted an N because I want them to stand for nuclei, the number of nuclei that we have there at the beginning and the number of nuclei that might be left after a period of time has passed. Okay, so N at time t divided by N at time naught was equal to minus KT. Again, this reflected first order decay, first order kinetics. We also derived an equation from this and said, well, what if we look at the time required for half of it to disappear? We defined that as the half-life. Remember, for first order decay, half-lives are like a fingerprint. Every reaction has its own unique half-life and it doesn't change. Well, it turns out that's because the half-life is related to the rate constant. I should point out, they quit calling it the rate constant in this chapter and started calling it a decay constant. But again, it's the same thing, except that we're looking at radioactive decay. If you recall, the natural log of 1/2 was minus 0.693, so the minus signs cancel out, and 0.693 over K equals the half-life of a radioactive isotope. All right, well, these are the only two equations then that we need to go back from our kinetics chapter and snag because, again, first order kinetics. All right, well, let me do a couple of the homework problems and show you how these are both applied. Okay, in this example, I tried to incorporate both of the equations that we're going to use for first order kinetics. And so I chose a beta emitter, phosphorus 32. And suppose, and we know a lot about phosphorus 32, it's got a half-life of 14.3 days. Suppose I'm working with phosphorus 32 and I order a sample of it. It comes in on Monday morning. All right, so I've got a sample that weighs 0.28 grams of phosphorus 32 Monday morning. And my question is, by Friday, at close of business, 4.3 days later, how much of it would actually remain? Because it's got kind of a short half-life, only 14.3 days for half of it to disappear. So my question is, if I just get the delivery on Monday morning and I let it sit till Friday night at 5, 4.3 days later, how much of that stuff is really left? Okay, well, when we try to figure out, well, how much stuff is left, we'd have to use the ln of n at time t over n at time naught. And actually, we don't have to put the number of nuclei in here. We could put the number of grams in because it's just a ratio of how much is left at time t to how much I started with. But that's going to be equal to minus KT. And we want to know how much of the phosphorus 32 would be left after 4.3 days has passed. We know how much we started with. What we don't know is K. But again, if I gave you the half-life of the isotope, then for all practical purposes, I've given you the value of the rate constant. Because remember that K is going to be equal to 0.693 divided by the 14.3 days. Let me get my calculator here. Hold on just a second. Okay, 0.693 divided by 14.3 days. Oh, I can't even see. 0.0485. And that would be days to the -1. Okay, can you see that on the screen? Yeah. 0.0485 days to the -1. So now I have the K value. I have the amount of time that's going to pass, 4.3 days. I know how much of the phosphorus 32 I'm starting with. That's N at time naught. I want to know N at time T. All right, well, let me make a little bit of room here now that we've got everything, and we'll plug in what we know. Okay, so I plugged in everything I know. The natural log of the amount of phosphorus at 4.3 days that would be left, divided by what I started with, would have to equal minus K, which we figured out down here using our half-life, the minus 0.0485 days to the -1, times the amount of time I'm going to let elapse. All right, well, let's go ahead and crunch everything that's on the other side of that equal sign and find out what the ln of NT over the 0.28 grams equals. Well, it turns out to be minus. Might as well put the minus sign in there right now. Let's see, 0.0485 times our 4.3 days came out 0.2086, negative 0.2086. That sounds funny. Let me try that again. I recognize that number. 0.0485 times our 4.3. Yes, negative 0.2086. All right, now, to get rid of the natural log, remember we have to take e to this power. And that turns out to be 0.812. So that means NT over 0.28 would equal e to that minus 0.2086, which comes out 0.812. Well, then it makes it pretty easy to figure out what N at time T is. It's going to be the 0.28 times the 0.812. That's going to equal 0.227. I guess we could go 0.23. So 0.23 grams would actually remain after the 4.3 days has passed. Now remember, not even an entire half-life has passed. Only 4.3 days, the half-life was 14.3. So we didn't let a whole lot of time pass, but you saw that, sure enough, there was a decrease in the amount of phosphorus 32 from the original 0.28 grams. It decayed down to 0.23 grams in that 4.3 days. This is typical of the type of problem they're going to give you. They'll give you the half-life or some way to find the value of K, and then they'll simply have you do either give you the time elapsed and ask you for how much is left, or they'll tell you how much is left and ask you how much time has elapsed. So again, they'll come at it from one of those two directions. As a matter of fact, let's do one more that does that. Okay, here's another problem that actually incorporates both of those equations, the first order time concentration equation and the half-life one. This one said, suppose we had a sample of iron 59, and it registers, we put it in a Geiger counter, it registers 125 counts per second in our Geiger counter, and then 10 days later we measure the same sample and it's dropped to 53 disintegrations per second. From that data, could we calculate the half-life? Well, again, not too tricky here. We can use the first order time concentration equation and use the beginning and ending counts and the amount of time that's elapsed to figure out the rate constant K, the decay constant. That would be the only thing missing then from the first order time concentration equation. Once we have the value of K, then it's a simple quotient, 0.693 over K, would tell us the T1 half, the half-life. All right, so that's our plan. Now that you've got this that you can kind of go back and look at, let me erase it and we'll put everything into the equation. Okay, well here we go. We plugged everything in that we know. We've got the natural log of the activity at time t. After 10 days has passed, it dropped to 53. From the original was 125 disintegrations per second. That's got to be equal to minus kT. And again, we've established the time elapsed was going to be 10 days. All right, so then if we rearrange this, K is just simply going to be this natural log of this quotient divided by the minus 10. We'll put the minus sign over there. All right, well, let me go ahead and quickly crunch this. Let's see, 53 divided by 125, and take natural log of that, divide it by the 10, and drop that negative sign. I ended up with a 0.0858 days to the minus 1. And again, that's because days is down here in the denominator, and this is a pure number, this natural log. All right, so we solved for K, the decay constant. Again, one more step should give us the half-life. This is 0.693 divided by K. In this case, the K value is 0.0858 days to the minus 1. So let's do that. 0.693. I ended up with 8.08 days as the half-life of the iron 59. And again, we could figure that out pretty easily. All we have to do is monitor a radioactive isotope at one point in time and see how much it decays to another point in time. And from that, we can plug it into the first order time concentration equation, find K, and from that we can find T1 half. And as a matter of fact, for our lab, our very last lab that we're going to do on radiation, we're going to give you some fake data here for an unknown isotope. And we're going to have you graph it and figure out from the slope of that graph, figure out the value of K. Once we have the value of K, then we can find the T1 half of this unknown isotope. So that'll be the exercise that's coming up for you with the radiation lab. All right, well, now that we've looked at the kinetics of radioactive decay, and again, there's a couple things about radio dating that are in the homework, where they use carbon-14, has a long half-life, 5,700 plus years. And so consequently, they'll give you some data on, say, fossils that they found, what the activity was at the beginning, what the activity was at the end, and have you figure out, well, how old is that fossil? How much time has elapsed? So again, it's just using the first order time concentration equation, but in this case, you'll be solving for the time that it took for the radioactive decay to fall that much. All right, well, now we're at the end of the chapter, and we're going to talk a little bit about nuclear fusion and nuclear fission. And something I alluded to earlier in part 1 was the binding energy that seems to hold the nucleus together. I mentioned that the mass of a stable nucleus is always less than the sum of its parts, and that little mass defect actually represents the energy that's holding the nucleus together. All right, so let's look a little bit at this concept of binding energy. Okay, well, this topic on binding energy, and I mentioned the idea that if you were to look at a stable nucleus, as a matter of fact, this is what I started with, this statement, the mass of a stable nucleus is always less than the sum of its parts, its nucleons. And that missing mass, that mass defect, represents the energy that's holding the nucleus together. Now you're thinking, well, missing mass and energy? Well, Einstein pretty much defined a mass-energy equivalence with his equation E equals mc squared. So if we were to look at this mass defect between the stable nucleus and the sum of its nucleons and put that in here as a change in mass, we could actually calculate then the amount of joules of energy that are actually created to hold that nucleus together. All right, well, let's do a quick example. Now you got to be careful of the units here. The speed of light goes in meters per second. In order for this to come out in joules, that mass defect has to go in kilograms. All right, well, let's just take a simple stable nucleus, something that we've measured its mass very accurately, and we'll look at the sum of its parts and compare those two numbers. Now, I should point out that we've got the masses of several nuclei and masses of the protons and neutrons listed in a table in your book. These were all determined using a mass spectrometer device invented back at the turn of the century, back in the early 1900s by J.J. Thomson. And so again, we've got very accurate masses on the nucleons and very accurate masses on the nuclei of stable atoms and unstable ones. So it's not too big a task, more of an arithmetic problem, to just look at this mass defect, the difference between the stable nucleus and the sum of its parts. All right, well, enough talking. Let me do an example. Okay, so here's a typical binding energy problem. Suppose we look at stable isotope of lithium, lithium-7. Well, lithium-7 contains 3 protons and 4 neutrons, and its nucleus weighs, according to the mass spectrometer, 7.01600 AMUs, all the way out 5 decimals. Now, an important conversion factor that we're going to use in doing these problems is this. 1 AMU, if we wanted to convert it into grams, is 1.66 10 to the minus 27, actually kilograms, because that's the way we're going to use this. All right, so you might want to keep that little constant there handy. I got it by taking 1 over Avogadro's number. So essentially that converts AMUs into grams. All right, so let's hold that aside. Now, I looked up the mass of protons. Protons weigh 1.00728 AMUs each. Again, mass spectrometer numbers, very accurate. 3 of those would weigh 3.02184 AMUs. Now remember, this is what the lithium nucleus weighs up here, 7.016, but now I'm adding up the sum of all of its parts. Well, it also contains 4 neutrons. Well, 4 times the mass of a neutron, which again, a table in your textbook has all these masses for you to do the problems. I think I assigned maybe 2 of these in the homework. If we took 4 times the mass of a neutron, we get 4.03466 AMUs for a grand total of 7.0565 AMUs for the parts. Now again, this is just the nucleus. Here's, however, what the nucleus weighs. So there's a clear mass defect. The nucleus weighs less than the sum of its parts. That missing mass essentially has been converted into energy. That's the energy we would have to put in order to separate the nucleus back into its parts and re-add that mass. All right, so let's find the mass defect, convert it into kilograms using our little conversion factor up here. Then we can use Einstein's equation to figure out, well, how many joules of energy are actually holding that nucleus together. All right, well, let me find the mass defect first. Okay, so here's our mass defect. This was the mass of the lithium nucleus, the 7.016 AMUs. Here was the sum of the parts, 7.0565. So the difference shows a mass defect of 0.0405 AMUs per nucleus. All right, well, let's use Einstein's equation then. Well, first, I guess we've got to convert that into kilograms. We really need to use it in kilograms. So let's take the 0.0405 AMUs that seem to be missing. We'll multiply that times 1.66 10 to the minus 27 kilograms per AMU. All right, and that'll give us our mass in kilograms. All right, so let me get rid of this. Okay, so 0.0405 times 1.66 10 to the minus 27th kilograms. It says that we're missing 6.723 times 10 to the minus 29th kilograms of missing mass. Okay, well, now we can use Einstein's equation. We can convert that actually into joules. So the energy is going to be the change in mass equals mc squared. So we'll take the change in mass, 6.723, 10 to the minus 29th kilograms. The speed of light, 3 times 10 to the 8th meters per second squared. Meters per second, and we're going to square the speed of light. Notice the units come out kilogram meter squared per second squared, and by definition, that's a joule. So let's go ahead and take this times E squared. And I get 6.05 times 10 to the minus 12 joules. Now again, that's what's holding, that's the energy that's holding together that lithium nucleus. Just one nucleus. If we had an entire mole of lithium nuclei, we could figure out the binding energy per mole just by multiplying this by Avogadro's number. You can see it would become a significantly large number holding that nucleus together. So this is really quite a bit of energy, quite a bit of mass that's missing when a stable nucleus comes together. And apparently that mass has been converted into the energy that's holding that nucleus together. Now, what's more important is not the total amount of energy for the nucleus. What if we were to divvy this binding energy up among the 7 nucleons that lithium actually has? I don't have its symbol up here anymore. But lithium, remember, has 3 protons and 4 neutrons, so there's 7 total nucleons in that nucleus. What if we gave each of them an equal share of that binding energy? Just spread it out among those 7. And we'll define this as the binding energy per nucleon. All right, well, let's do that real quick. All we have to do is take this number and divide it by 7. We'll just give everybody an equal portion. All right, let me get a little room here. Something revealing comes out of this. If we were to say, okay, 6.05 times 10 to the minus 12 joules, and that's per nucleus, but one nucleus contains 7 nucleons. That's for this particular isotope because we're looking at lithium-7. All right, so it had a total mass of 7 nucleons, 3 protons, 4 neutrons. So if we divide that number by 7, we end up with 8.64, 10 to the minus 13 joules per nucleon. So that's how much each proton and each neutron share is of the binding energy. Now here's what became very interesting about this binding energy. Once we started to look at this for all the different stable nuclei, and you know how we are, we love to graph stuff, it didn't take long for us to see that there was a trend in the binding energy per nucleon if we looked at the array of elements that we knew. All right, well, let me make a little bit of room here and I'll show you the graph. Okay, you'll see this graph in your textbook. Once we compiled lists of the amount of binding energy per nucleon for all the stable nuclei, if we plot them versus their atomic number, we find that down here at the beginning, hydrogen number 1, it doesn't have any binding energy because there's only one nucleon in its nucleus, a proton, and it weighs exactly what a proton weighs, so there's no mass defect. But by the time we get to helium, sure enough, it has some binding energy. All right, so the binding energy increases as we continue to go atomic number by atomic number. And so it's getting more and more stable as we go this way. The nucleus becomes more and more stable. It finally reaches a maximum, though, and then begins to fall off. Now, this is kind of an important breaking point. And if I were to ask you just to guess, well, what element do you think is the top dog there in terms of binding energy per nucleon? Logic might dictate that, you go with something like lead. Lead's stable nucleus, got magic numbers, even stuff. Surely it's up there. It turns out that this breaking point happens at iron 56. That particular isotope has the most binding energy per nucleon, the most stable nucleus. Now, the importance of that breaking point is this. Things get more stable as they approach iron 56. So that means that elements that are over here, say like uranium, if it could break apart into smaller isotopes, maybe up here, they would become more stable and release that energy. So that means anything north of iron 56 is a good candidate for a fission reaction, where you split an atom into two smaller atoms. Well, those smaller atoms, as long as they're on the north side of iron 56, are going to be more stable than the uranium was. Consequently, that energy gets released. Well, fission reactions do exactly that. When uranium splits into two smaller daughter isotopes, energy gets released because those daughter isotopes are more stable than their parent was. However, what's happening on the south side of iron 56? Well, down here, it turns out that if we could join, say, two nuclei together, like add these two, smack them into each other, and maybe fuse them into an atom that's larger, it just got more stable and energy is released. So that means anybody on this side of iron 56 is a good candidate for fusion reactions, not fission. And the dividing point comes right there at iron 56. So although iron 56 itself is not very notable, it does mark that division between fissionable material and fusible material. Now I do want to show you a few of the reactions here. And by the way, I did put a binding energy problem on one of the green sheets, and I think I had you calculate binding energy per mole. So at the very end, when you get that little number of joules, you have to bump it up by Avogadro's number. So again, just be careful of the units. And I think I put one there on the green sheet, and there may be one or two that are in the text homework. Okay, well, I want to show you a few of the reactions that uranium undergo in a fusion reactor, and a little bit, in a fission reactor, and a little bit about nuclear fusion. And then we'll close with just a few practical applications of radioisotopes, for instance, in medicine. All right, well, let me clear the screen and we'll look at some fission and fusion reactions. Oh, one thing I wanted to mention about the binding energy problems, the book likes to use the unit MeV, mega electron volts, for binding energy instead of joules. And so the conversion factor that you'll need in case you want to convert units so that it matches up with our textbook is that 1 MeV equals 1.602 10 to the minus 13th joules. So hopefully that'll resolve any unit issues that you have with the homework problems. All right, well, let's look a little bit then at fusion reactions and fission reactions. Okay, here's a little bit about nuclear fission. For instance, light water reactors that use uranium fuel rods. Basically, when uranium undergoes radioactive decay, it's because it's being struck by a neutron. Because when it decays, it creates neutrons, and those neutrons then strike an adjacent atom and again begin the fusion process again. All right, so if we look at a uranium-235, 92 is its atomic number, smack it with a neutron, it turns out it undergoes 3 different mechanisms by which it'll split. Sometimes it splits into a krypton 94 and a barium 139, but it also spits out 3 extra high-speed neutrons that then will crash into other nuclei and cause them to split. So you can get kind of a chain reaction going that way. The other mechanism is that the uranium sometimes splits into rubidium 90 and a cesium 144 and 2 neutrons. Its other pathway that gives it 2 isotopes are strontium 90 and xenon 142 and an additional 2 neutrons. So it turns out that if you've got a little chunk of uranium sitting around the house and a neutron hits it, or from internally, as it decays spontaneously, it spits out some neutrons, those neutrons are going to crash into other nuclei and again cause them to split. So this is why uranium just continues to decay, decay, decay. And you can release way too much energy too fast if you've got too large a chunk of uranium, beyond what they call the critical mass. Now, each one of these reactions gives off a significant amount of energy. If you were to look at the total mass of the nuclei on this side compared to the uranium, there's a definite mass defect. and that mass defect comes out as an enormous amount of energy when this fission reaction occurs. All right, well, let me just show you something about light water reactors and nuclear weapons and critical mass. Okay, well, this concept of critical mass, pretty simple to explain. The idea is that uranium, as it decays, it gives up other neutrons, and those neutrons smack into other uranium nuclei, and then causes them to split. And sure enough, when they split, they give off more neutrons, they hit another, it goes up exponentially. So the chance of a chain reaction where this could get away from you and create more energy than you could handle is significant. All right, well, it turns out that if your piece of uranium is really small, the chances are neutrons are going to escape the piece. More neutrons will escape the piece than will actually strike another nucleus. Remember, the nucleus is real tiny and there are lots of empty space, so there'd have to be a significant path for the neutron to take before the likelihood is that it'll hit another nucleus before it gets outside the piece. But if you have a large chunk of uranium, now the chances of a chain reaction are significant, because the likelihood that a neutron from, say, in the center would escape the piece pretty slim. It's going to hit another nucleus. It's going to create more neutrons. That's going to go exponential. This thing's going to suddenly explode with energy. All right, so as long as you keep the masses of the uranium at subcritical levels, well, then no chance of a chain reaction. You reach that breaking point where the piece gets too big. Well, let's see how this applies to light water reactors. Okay, well, here's my simple picture of a light water reactor. Essentially, they have control rods made up of uranium slid into the reactor core here. And the uranium is subcritical, but it's exposed to other uranium fuel rods that are very close to it. So neutrons from one can strike the other and could run the risk of getting away. All right, so in order to control the rate at which the uranium decays, they put in cadmium control rods in between the uranium fuel rods. Well, these cadmium control rods are like little neutron vacuum cleaners. Cadmium's notorious for sucking up neutrons. Okay, so it turns out that if you drive the control rods in and limit the exposure of one fuel rod to the other, you can slow down the rate of decay. All right, and then you pull the control rods out, suddenly you expose the rods to each other, neutrons are going from rod to rod, and the reaction begins to increase in rate. And so, again, you can kind of dial this in. Well, then they use the heat generated by that to heat up water that surrounds the reactor core. They turn it into steam and run turbines, make electricity. All right, so simple enough concept. All right, now one anecdotal thing here, though, that I should mention. The first light water reactor that we came up with, 1955, was overseen by the Navy, and I think it was in Pennsylvania where they built it. And theirs was pretty rudimentary. They had a big tank, they had the uranium in, and then they had control rods actually connected with ropes and pulleys up above. And they had a guy with an axe, just in case the reactor would get away from him, that was supposed to cut all the ropes and drop all the control rods into the reactor to shut it down. They did have a few close calls, apparently, and it was revealed later that there were a few days when they were sweating that they couldn't get the control rods to lower quickly enough into the reactor, and it could have easily gotten away from them and taken out Pennsylvania. So it was fortunate, at least for the Navy, that none of those things occurred. But this is kind of the basis for the light water reactor, is that tipping point between subcritical masses of uranium and critical masses. All right, well, let's look a little bit at a bomb. Okay, well, this has got to be the simplest picture of a nuclear weapon there ever was. But essentially, if you want to cause a chain reaction to occur, which would cause a nuclear explosion, you need a couple subcritical pieces of uranium-238. Now, if you arrange them in such a way that, they're far apart from one another and the neutrons from one can't reach the other, then it's not going to reach a critical mass and it's not going to have a chain reaction. So you've got these subcritical pieces of uranium. Well, when you do want them to meet, put an explosive charge behind one of them and just drive them into one another. All right, well, at that point, now you've got a critical mass of uranium-238, and a chain reaction begins, and way too much energy is released way too fast. So I guess the takeaway from this is that if you got a bunch of uranium-238 laying around the house, try to keep them in little small chunks and just keep them separate from one another. That's probably the best idea. All right, so now we've looked at some fission reactions. Particularly, we looked at uranium and three mechanisms by which it can actually split apart. And there are many others that the book lists. They show you a whole bunch of fission reactions because remember that graph that shows the plateau or the peak at iron 56? On the north side of that was all that good fissionable material. And so consequently, there's a lot of candidates over there that can be broken up into smaller daughter nuclides that are more stable, consequently releasing energy. So again, the homework problems you'll run into regarding that, they'll show you a fission reaction and just leave out a missing piece. Well, again, you just have to add up the atomic numbers and figure out what that missing piece is. So there's not much to it other than the fact that they're just trying to illustrate to you several different potential fissionable type reactions. Well, on the other side of that graph, recall, were good candidates for fusion type reactions. And so let's take a moment to look at some of those. Okay, nuclear fusion reactions. Remember, we talked about this with the graph of binding energy, that elements that are on the lighter side, if we fuse them into a larger nucleus, that essentially that nucleus has more binding energy, and if it becomes more stable, then that energy gets released. And sure enough, you can fuse, for instance, 2 deuterium. These are the isotopes of hydrogen that have an extra neutron in the nucleus. They have a proton and a neutron, so they're called deuterium. Turns out 2 deuterium atoms, if you crash them into each other using a particle accelerator like they have at CERN or we have up at Fermi Labs, if you smack them into each other, you can make a helium atom, and it'll pop out an extra neutron and a significant amount of energy. But these particles have to be moving pretty fast, and you have to have them at extremely high temperatures. Now, this other fusion reaction is a deuterium and a tritium. This is a hydrogen with 2 neutrons in it, very radioactive. Turns out those two actually, at the lowest temperature, you can get them to fuse into helium and a neutron. And actually, it gives off more energy than you have to put in to accelerate them. However, it has to be at 100 million degrees centigrade, all right, for this reaction to actually get kick-started. All right, so even though you get a little bit of energy back from this, it's hard to contain it. It's like taking the sun inside your house and trying to hold it still. You have to hold this reaction in a huge magnetic field, and the energy required to maintain that containment field exceeds the amount of energy that you're getting from the fusion reaction. So this is where the issue is now. We could get sustainable energy from a fusion reaction if we can figure out how to contain it. All right, well, now we've looked at fission reactions that happen with the heavier elements to make lighter ones that are more stable. And then down on the south side of iron 56, we looked at fusible material that you can fuse together to make, again, more stable daughters and release some energy. So fission versus fusion. All right, well, let's look now, to wrap this all up, at a few practical applications of radioactive isotopes. Okay, well, beyond the obvious medical uses for radioactive isotopes that we've found over the years, chemists have used this for a long time to analyze different mechanisms, different pathways that molecules might take through a system. For instance, in human physiology, it's difficult to just strap a video camera to an organic molecule and follow it through its path through something like, say the Krebs cycle, or some metabolic pathway that happens in human physiology. So a lot of times what they'll do is they'll put a tracer in there. They'll build the molecule, but they'll use some carbon-13s in there as a label to label part of the molecule. Then later, after they follow it through the organism, whether it be a lab rat or a plant, they can actually x-ray and find out where that carbon-13 ended up. So it's actually just like putting a cowbell on a molecule and turning it loose out into the field and find out where it ends up. All right, carbon-13's been a very handy then analysis tool for organic chemists. In addition, they do things like isotopic dilution to figure out things. I thought this was kind of an interesting way to find your blood volume. They put a radioactive isotope, very short half-life, of sodium into your system, which obviously is not going to hurt you. You're littered with sodium atoms. But they'll put a small amount injected into you, let it circulate. Then they'll take a small sample of blood and see what the molarity is now of the sodium after it's been diluted in your entire blood system. With that, they can estimate the volume of blood then that you have in your entire body. All right, I just thought it was kind of a clever way of using radioactivity, a radioactive tracer, to figure out something like blood volume. All right, one of the other things that's kind of interesting is neutron activation. It turns out that, and I think the example they used in one of the textbooks was taking a hair sample, and they were looking for arsenic in the hair. Well, it turns out that arsenic, if you bombard it with neutrons, it becomes a metastable form of arsenic, like the cobalt 60 that I mentioned, I think, in part 1. If you inject neutrons into it, suddenly you create an isotope that's neutron to rich, and so the neutron to proton ratio is too high, and you've created a metastable nucleus that usually will belch out either a gamma photon or a beta particle. Now, the gamma photons that come out, the frequency of those photons is usually unique to what element it was you just bombarded with the neutrons. All right, so it turns out if you're looking for arsenic in hair at very low levels, let's say, they'd shoot a neutron beam in, the arsenic becomes metastable and emits a gamma frequency that's unique to the arsenic. So you can use that to analyze for certain elements in a situation where the levels are so low that you can't do it by conventional methods. So again, another practical use of radiochemistry. Well, let me erase this and I'll show you just a few medical isotopes and we'll wrap this up. Okay, well, just a few examples of radiotherapies that they use in nuclear medicine. Technetium-99, metastable technetium-99, is probably the most widely used. I mentioned it, it has a tendency to accumulate in tumorous tissue. And so consequently, you can get good images of tumors. It's a gamma emitter, so it shows up really nice on a CT scan or an X-ray. Now, iodine-131, also used for the thyroid. They also use this like if you tear a joint or something and they want to get an image of the tear, they'll inject iodine-131 in there. And it shows up really nice. It's a beta emitter. And it'll show up nice on X-rays or on CT scans. As a matter of fact, I tore a knee one time, and this is 40 years ago, and I went in to have the X-ray done, and at the time they weren't doing the CT scans on it; they were just doing an X-ray, and they drew the synovial fluid out of my knee, which looked kind of like motor oil. You know, they drew quite a bit out of there, and I asked them if they were going to put that back. It looked important, and they said, "No, you'll make more. Don't worry about it." So anyway, then they injected some iodine-131 into my knee and got me up off the table and had me walk around, and I could hear it squishing around inside my knee. And then they blew it up with air. They pumped air in there, so it just looked like a big balloon around my knee. Well, then they got me up on the table and torqued the leg around while they were taking X-rays of it, and I could see on the screen, I could see where the tear was in the meniscus in my knee. And again, the iodine was just kind of shooting through there. Well, being curious that I am, I asked him, I said, anybody know what, the half-life of the iodine you're using? And nobody in the room knew, which was a little unsettling. I think if you worked in nuclear medicine and you were working with radioactive isotopes all the time, you'd really want to know what the half-life is of the isotope that you're working with. Well, anyway, it turns out iodine-131, 8 days. So I was radioactive for, several days after that. And my knee, I could hear it squishing every time I took a step for the next couple of weeks until that iodine finally got reabsorbed and more synovial fluid got created in there. But they use iodine-131 quite a bit. Iron-59 for blood analysis and spleen analysis because it has a tendency to accumulate there. 44.5-day half-life though. And so again, you just got to be aware of the fact that when they're using medical isotopes like this, there's not only a physical half-life for the actual isotope, there's a biological half-life, meaning how fast will your body flush it out, regardless of how long it might last. And sometimes that's much faster than the actual physical half-life of the isotope. And so you run much less of a risk of exposing yourself to radiation that way, if at least your body is going to eliminate it quickly. Now this last one, this thallium-201, they use this for the heart. They're kind of doing away with this. Thallium, a radioactive isotope, does accumulate in damaged heart muscle tissue. So they'll do stress tests where they'll inject you with a little thallium and have you run on a treadmill and then take an X-ray, and the thallium will accumulate in the damaged heart muscle and consequently it shows up nicely on the X-ray. Problem is that thallium is a neurotoxin. It's the main ingredient in decon rat poison, and so it attacks your nervous system, and I think they're doing away with it just because of the unwanted side effects that may have happened with the thallium. Now, some places are still doing thallium stress tests, but I think that the days are probably numbered. I think they'll find some other either less or more dangerous thing to do to us to figure out if our heart is okay. All right, well, let me get rid of this and we'll kind of draw a few conclusions from this chapter and wrap it up. Okay, well, that's it for our radiation chapter. I think I'm going to do one more little lecture on organic chemistry, a short one, just to wrap up the semester, and that'll pretty much do it. Now, the topics that we covered in chapter 21, we started off with nuclear stability, you know, the concept of, well, why would a nucleus want to spit out parts of itself? And again, I gave you some generalities about even numbers of protons and neutrons likely being stable. The magic numbers were clearly very stable. And we showed you circumstances that would bring about instability and probably the ejection of particles, for instance, like having more than 83 protons. So then we started to look at mechanisms, the types of radiation. And that's where we went over alpha, beta, gamma, positron emission, electron capture. So be able to balance out those nuclear equations. Again, it's not a big issue. It's added and subtracted whole numbers, so it's not like I said, a daunting task to figure out how to balance those or to figure out a missing daughter isotope in one of those equations. And again, we're not necessarily going to ask you to make predictions about those. We'll just give you a nuclear reaction, leave out the missing piece, or tell you that it's going to be an alpha emission, and so you already know what the particle is on the right side of the arrow. Just figure out what the daughter isotope would be. And then we talked about the band of stability. And, you know, kind of a nice circumstantial graph, circumstantial evidence for where the stable nuclei like to be. So consequently, any isotope that's outside of that band is either going to undergo beta emission if it wants to reduce its number of neutrons, or electron capture and positron emission if it wants to increase that neutron to proton ratio. And so again, that graph was very revealing about making predictions about isotopes. Then we talked about the kinetics, and this is where the number crunching really came in. We have to go back and revisit that first order time concentration equation. And so they came up with some clever ways to, you know, shake the dust off that equation for you and figure out, for instance, how much time has passed for an isotope to decay from here to here. Or they'll tell you how much time has passed and say, well, how much isotope is left after that much time? And again, we introduced the relationship between T1/2, the half-life, and the rate constant, the decay constant. But again, it's the 0.693 over K, so it should be familiar. And we looked at the binding energy, mass defect, and again, this is Einstein's E equals mc squared equation. Just be careful, you got to have the mass defect in kilograms. That's the key there. And your energy will come out in joules. I mentioned that the book likes mega electron volts, MEVs, and I gave you the conversion factor to convert joules into that in case you need to use that conversion. But again, make sure you take a look at a couple of those. I'll put one on the test next time. And then we looked at fission and fusion reactions and kind of made a plot of binding energy per nucleon to show, well, where are the good candidates for fissionable material and where are the good candidates for fusible material. And so, again, just make sure you're aware of that discussion. And then the last little part was just anecdotal, good dinner conversation about applications of different isotopes that we use in medicine. Okay, well, we're pretty much at the end of the semester. I'm glad you all held up so well. Like I said, I'm going to try to get one last little lecture on organic chemistry here, and pretty soon I'll be sending out that take-home exam, the take-home exam, that'll be due at the final. But anyway, I'll be sending you a flurry of emails to explain all of this as we wrap this up and tie a bow around it. But congratulations to all of you who managed to survive this semester. This has been different for everybody, but good job. All right, well, I'll see you at this next little lecture, and just keep your eye on your email. So long.